So, in this presentation, first of all, okay, as Peter said, I am Valentina Bertana. I would like to thank him very much, and also I would like to thank also Fachberger Hans, which created this contact. In this presentation, I'm going to show you some work we are carrying on at Politecnico di Torino about electrically conductive polymers for additive manufacturing. First of all, only to give you a context, Politecnico di Torino is located in Piedmont, a region in the north of Italy, and in Piedmont, in Politecnico di Torino is the, how can I say, head office, okay, is the big university hosting thousands of students and researchers. And in particular, I work at the Department of Applied Science and Technology. This department coordinates many other laboratories, more than the ones that are directly inside the department. And one of these laboratories is the Key Lab, which is the lab where I work most, which is located in Chivasso. And Chivasso is a small town, only 30 minutes far from Turin. And so we always have a strength connection. At Keylab, we have a clean room. So indeed, a clean room divided into 3 different classes. And so we have clean room facilities for the design and fabrication of micro devices. Micro devices means both microfluidic devices and microelectronics. Our work is also focused on technology transfer. So we work together with the university and also with the industrial partners. Education. Indeed, we host every year students from both master or bachelor courses or PhD students which want to try this laboratory experience. Inside Keylab, we have also a 3D printing lab, and the 3D printing lab is equipped with 2 inkjet printers, one FDM printer, 3D plastic sintering, so a 3D printer based on powders, and 2 microstereography printer, one which is commercial and the other one is custom. The custom one is this one I show you here on the right. It was fully developed by Microlab Optoelectronics. And why I say that it is custom? Because we managed to set different type of parameters, and this allows us to work very well with novel materials. Indeed, at Politecnico, in my department, we have a lab more dedicated to polymers and to the modification of polymers, which can be useful for 3D printing. And so with this printer, we managed to print them by changing, for example, different parameters regarding the laser, different parameters regarding the etching strategy, so the movement of the laser of this laser, and different parameters regarding the mechanics. Indeed, this is probably I didn't tell you, is a top-down SL printer, stereography printer, and we are able not only to change the parameter related to the laser, but also related to the mechanical part, let's say. So this means that also depending on the, for example, on the material viscosity, we can change both the movement of the platform inside the material or the movement of the recoater along the printing surface. So going back to the design and fabrication of micro nano devices, so design and fabrication of, for example, lab on a chip. I choose this short sentence, but I think that it is very important to take this fact in mind. And it says that a lab on a chip is not simply a network of microchannels, but it also includes function depending on the application, such as pumps, valves, sensors, and electronics. Indeed, we every day face this issue. So we develop sensors, we develop microfluidics, but sometimes there is a problem in connecting these two, and moreover, microfluidic without some kind of sensor of some kind of electrical connection doesn't work properly. So we have started to develop the 3D printing of microfluidics, and we wanted also to add 3D printing of functionalities. In this case, we have worked by using two different strategies. In one case, we wanted to add metal nanoparticles to our 3D printing resin. And in the other case, we have tried to add intrinsically conductive polymers. In the case of metal nanoparticles, I have started in particular my work by a work from my colleagues, and in this work they have obtained the 3D printing of silver nanoparticle ink, silver nanoparticle resin, not starting from silver nanoparticles directly, but from a precursor. In this case, the matrix was composed by PEDOT, which is the hosting matrix, the photocurable matrix, PEDOT plus photoinitiators, and then they added a silver salt. In this case, it is silver nitrate. So as you can see, the object just printed appears with this reddish, yellowish color, and this is for the use of a particular dye. In this object, we have silver salts. So silver nanoparticles are not yet present. But by applying a right energy dose, in this case by irradiating the object with UV light, they obtained an object which is full of nanoparticles, silver nanoparticles, and it has this silver-like aspect. So the idea was to use the customized stereolithography printer to directly print paths on this object without generating silver nanoparticles in the whole object. And so this, if it is something, okay, these are the first tests. Here we can say that in the very beginning, we have simply started to create this silver strand on a previously printed layer of this resin, which was polymerized. And we immediately realized that the more energy we applied, the more these silver strands were well visible. And so more silver nanoparticles were generated. So in our process, the first step was to polymerize, so to 3D print the object. And the second step was to generate the silver nanoparticles, which were generated from the silver precursor. The very interesting fact about this was that we used the same equipment, so the same stereolithography customized printer and the same material, the same resin, but by changing the energy dose which was given to the material, we obtained two different behaviors. So we have tried to print a very simple track, let's imagine a part of an electric circuit, and the results were really good, but unfortunately, we observed that the resistance was of few megaohms. So very high resistance, not enough, not good to obtain an electrically conductive path. And asking why this happened, we decided to observe the generation of silver nanoparticles in the bulk. So observing a cross section, so imagine that you cut this path here and you observe the cross section, we realized that if on the surface, which is this one, the surface of the path, we can see many silver nanoparticles, inside the bulk, so going in depth of the strand, we observed that not so many nanoparticles were generated. They were distant one from the other, so the percolation threshold was not reached, and the thickness was really small. It is only 1 micron thickness from the surface seems to be the maximum depth at which silver nanoparticles are generated. So we decided to, for the moment, stop the studies about conductivity of this material, and we have started other tests because this material exhibited a very good antibacterial property. However, I wanted to show you this part of the work that we surely will deepen in the future by, for example, changing the silver precursor or changing other parts of the resin. Then going to the test with intrinsically conductive polymers, we have designed and synthesized this new resin, which is a resin made up by very few elements, which are PEDOT again, which is our photocurable matrix. And as filler, we used PEDOT PSS. PEDOT PSS is known to be a very high conductive, intrinsically conductive polymer. And in our case was extracted from a commercial water solution. From first test, we discovered that in this case, results were surely better. Indeed, if you see from this graph, reaching percentages of PEDOT inside the resin. So if you look at the horizontal axis, you can see the amount, the PEDOT weight inside the resin with respect to the whole weight of the resin. So when we have 35% of PEDOT or 45%, conductivity was really good in the order of 10 at -2 Siemens per centimeter. For sure, we are far from conductivity of copper. Okay, this was not our aim, but it could be enough to try to print something which is conductive. In our case, we choose to go on with the 35% PEDOT blend because it was printable, while in the other case, there was too much PEDOT and not enough hosting matrix to hold a stable structure. So first of all, we have worked to find the right printing parameters, as in every time we try to prepare a new material, we start with this point-by-point process. So first of all, find the right printing parameters. And here you can see on the left good printing accuracy with respect to the right, where the parameters were wrong. Here you can see in these two images the printing of a single layer. You can see that it is a transparent bluish material. The blue is due to the PEDOT PSS, and you can see also bigger flakes inside, which are they are PEDOT parts. These were the very preliminary test, and indeed after this test we have started to break a little bit more the PEDOT particles in order to obtain a more homogeneous and small dispersion of PEDOT inside the resin, and this would allow us also to print more accurate and with higher resolution printed object. After this, we created this very simple proof of concept, only to it is always helpful to make people understand that this resin indeed is an electrical conductor. We prepared this very simple circuit in which in one case the LED was connected to the battery through a insulant resistor, so in this case only made up by PEDOT, which is our hosting matrix, and in the other case we have our PEDOT PEDOT resin, and as you can see, in one case the LED is switched on and the other case is switched off. And then we have started to think about more complex tests to perform, complex studies for understanding which could be the application of this material. We work at the beginning on organic electrochemical transistors. These are devices, electronic devices, which can be used both as 2 or 3 terminal for biosensing, especially. We started from this because I have to say that at KeyLab we work from years also together with the National Research Council in Italy on the study of these organic electrochemical transistors. And we wanted to change and to move from the more standard planar bidimensional devices to a three-dimensional device and to see what happened. And indeed, we managed to obtain the 3D printing of these transistors. Here you can see not only the transistor, but the whole device. Indeed, we have the transparent part, which is like the vats, so where we put the liquid with the analyte and the main structure. And then we have two transistors, one which was designed to be with a channel 300 micron wide, and the other one with a 700 micron wide channel, also to study and to investigate the differences between the geometry and the performances of the transistor. At the end, we discovered that the 700 micron wide channel was better because the transfer characteristic curve was very good, good slope, and so this could be used for biosensitive and can be integrated also in other devices. And then we also investigated the properties of this material regarding its behavior with volatile organic compounds. And we printed this double helical system that you see here. We checked if something changed, in particular the conductivity, if this material was exposed to some common solvents, which are ethanol and acetone, and we discovered that when vapor exposure time increases, conductivity decreases. And so we could say that there is a lot of study to perform, but in a very first moment we can say that this kind of material can be useful to print or to add a functionality in order to detect the presence of these organic compounds also for long-term monitoring devices. So I would like to end by showing you some projects. Indeed, we don't work only with fundamental research, but we work, as I said at the beginning, also together with industrial partners, many industrial partners. And here I'm going to show you some of the project we have written, we are involved. Some were finished, some are at the beginning. This project, all this project involve additive manufacturing and functional materials to be put together to obtain something which is quite innovative. So I would like to end here. I would like to thank you very much for your attention. And if you have questions or if they arise later, feel free to contact me at my email. Thank you.